Hi everybody and welcome to the final module that appears on paper 1 of our physics course, the astronomy module SP7. Hopefully you finished SP6 on the assessment in it and we can move on with this one now. The first lesson in this unit is focusing on the solar system, which is where we live, but also how the understanding of it has changed over time and the reasons why it's changed over time. And who the key players were involved in coming up with these scientific models and the evidence to support them. So solar system is our first port of call in the astronomy module. Okay, so there's some people here with some interesting haircuts perhaps, but certainly before the days of photography, and these are the key players in our understanding of even today how the solar system fits together and how it works, some of whom you'll have heard of. But they were involved in some very key scientific developments in terms of coming up with models or strands of evidence. And you'll see in the text box, which is not coming out of where I'm sitting, thunderbolts and lightning, very, very frightening, as a not very subtle clue as to who one of those key players is for that. But again, important people and names to know. We need to know a bit of the history of science here as well, and some of the key players and their names and the models that they came up with and the evidence they provided. Hopefully you've had, for this lesson, you picked up from Frog or attached to the email, a lesson map, which is sort of like an overview with some key points and key diagrams for you to fill in and complete to sort of show your understanding and to build your understanding and knowledge about the solar system as we go through this topic. Okay, so you should have that. If you haven't, pause the video, go and get it, and we'll use that as a summary of the lesson. Okay, we'll have a quick quiz to start with, see what we already know, because I'm sure you bright people know quite a lot about this already, and therefore there's some things secure, but we need to make sure it's absolutely spot on to achieve the very best that we can on our GCSE in a year or so's time. So pause the video on a piece of paper somewhere, just jot down what you think the answers to these are, pause the video, and then when you've done it, resume the video. Okay, so hopefully you've got some words and things written down on a piece of paper to address these, and let's have a look. The nearest star to the Earth is the Sun. Notice it's a capital S because it's not any old star, it's the Sun, it's the name of it. That's our nearest star. Two types of body found in the solar system. Could have stars, sun, planets, dwarf planets, asteroids, comets, moons and satellites, so we need to know those. The name of the path is called an orbit. Again, I hope we knew that one. How many planets in the solar system? These days there are 8. Pluto no longer counting as a planet. 2 other planets in the solar system. Well, any one of the 8, and you do need to know those in order. So if you don't know them in order, you need to learn those as a little mnemonic. My very easy method just speeds up naming, and then it used to have Pluto. But that was how I remember it in order. What is a moon? A moon is a natural satellite of a planet. We often think of satellites as artificial metal things in orbit to spy on people or to provide Sky TV or whatever. But a satellite, the definition of a satellite is an orbiting body. So a satellite can be the moon, or a moon, as well as the artificial stuff that's put up there by people in there. One other body that orbits the sun, comets orbit the sun, asteroids and dwarf planets, Pluto for instance, orbits the sun as well. So any of those should be there. Why can we see the planets? Very important that we get this one right. They reflect the light from the sun. They are not luminous themselves, but they merely reflect the light off the star at the centre of the solar system, so they reflect the light. And the shape of an orbit is not quite circular, it's called elliptical. It's a kind of squashed, slightly oval shape, but we need to know that they are elliptical orbits, and we'll return to most of these things later. And an instrument that can use to study the stars and planets, it better had be the telescope from the earliest days to some of the more elaborate things and advanced telescopes that we see today, as you will see in a minute or two. We need to know those. So hopefully we got those, and if we didn't, we've got them now. Here's rather a nice little GIF showing the solar system in all its glory and motions and things that are happening there. You can see the various planets moving around in their years. It takes 1 year to orbit the sun completely. Some much slower than others, some much quicker than others. You've got Mercury, Venus, Earth, Mars, and you've got the asteroid belt, and then out to the gas giants beyond those as well. So nice little graphic there to show what we're studying in there as well. And you can see the phases of the moon changing in the bottom left as it orbits the Earth, and the phases change over its 28-day cycle for those. So in terms of objectives for the lesson, methods of observing the universe, we need to appreciate how they've changed over time, starting with the very earliest days with ancient Greeks, and then we're going to look at how the different bodies in the solar system, what makes up the solar system, and how it is about the structure, how is it arranged, how does it work, how that's changed over time, and then perhaps the most basic one, but you need to master it, is to know the names and the order of the planets that are in our solar system. So let's move on from this. Okay, now I'm going to look at the short video in a minute, featuring these work by these gentlemen, starting from way back, way back, where you've got just statues of people, into relatively more modern times, but once again, well before photography was invented. We're talking some serious history dates here. And as we see this video, I'd like you to consider, these are the questions that I want you to be thinking about as you watch this video. It's a good video, but these are the topics to think about. What did the ancient Greeks use to observe the stars and planets? They had, in ancient Greek, what they called philosophers, thinkers. And they were the earliest scientists, of course, thinking about how things worked, how things fit together, how the world around them worked. So the ancient Greek philosophers, looked up at the stars and the sky without pollution. Must have been a fantastic view of the sky in those days. And what was the problem? They came up with a model to explain what they saw, but what was the problem with their model? What was the issues with it? And then over time, that model changed, or after a long period of time, that model changed. But why did that change? We need to know who put up with that, and why explained it better, and what was the evidence for that model as well. So we're going to look at a short video now, good video, just sort of painting the picture of how the fundamental ideas of how our solar system evolved and how our solar system works was made. So bear with me for a moment while I rearrange the sources for this. Okay, so hopefully, without further ado, here we go.
If you've ever looked up at the sky and asked questions, then you're an astronomer. You're doing something people have done for thousands of years. Many say that astronomy is the oldest of the sciences, an attempt to explain the nature and the movements of the stars. And few areas of science can show us more clearly just how radically our ideas and our understanding can change over time.
The sun rises and sets every day like clockwork. But how do we know whether it's the sun that's circling around the Earth or the Earth itself that's rotating? From here on Earth, visually, both would look exactly the same.
It's not just the sun that moves either. Take the night sky. Like the sun, the moon rises and sets. And if we look at the stars, they all too appear to move, rotating around a single point. Again, there are two possible explanations. Either the stars or the Earth itself must be moving.
For the ancient Greeks, the answer was simple. The sun and stars had to be moving, not the Earth. If the Earth was moving, wouldn't we feel it moving? The ancient Greeks therefore built a model to describe their understanding of the way the heavens moved. They placed the Earth at the centre, with the moon and the sun orbiting around. And the stars were fixed to a distant celestial sphere, itself rotating around the Earth. Everything moved in perfect circles, a symbol of the gods' perfection.
But there was a problem with this system. In Greek, they called them planetos, meaning wanderers. These objects moved back and forth across the night sky. They didn't cooperate. They didn't fit the model.
To account for these wandering stars, the Greek model had to be modified. Convinced that the heavens moved in perfect circles with a fixed Earth at the centre, astronomers developed ever more complex models to account for what they saw. Circles upon circles upon circles.
But then there came an alternative model. A model proposed in the 16th century by the Polish astronomer Nicholas Copernicus and later perfected by the German Johannes Kepler, placed the Sun and not the Earth at the centre.
Here I have the Sun, Earth and Mars, with the Sun at the centre of the solar system and the Earth and Mars orbiting around it. Now, if I was on Earth and I took photos of Mars night after night against a background of fixed stars, let me show you what you'd see.
We see just what the ancient astronomers saw. Mars moves forwards and backwards across the sky. The planet does not really change direction, it is simply how we view it from the Earth against a background of stars. Those wandering objects we now know were not stars themselves but planets, and this elegant sun-centered solution could explain away the need for the old model's never-ending circles. Then, in 17th century Italy, the astronomer Galileo Galilei did something unprecedented. He built a telescope and he pointed it at the night sky. One of the many groundbreaking discoveries that Galileo made with his telescopes was that the planet Jupiter appeared to be host to 4 moons of its own, the first direct evidence that not everything revolved around the Earth. Our place in the cosmos was no longer special. In this new model, the planets orbited around the Sun, and this meant for the Sun and stars to move across the sky, the Earth must be rotating. Here is a clear example of how science works. Scientists use models that can explain what we see and experience, models that can predict how things will behave in the future. If a new model can better explain what we see, then it replaces the old. Of course, we've come a long way since Galileo first pointed his telescope. Nowadays, they've grown a little bigger. Telescopes like the Liverpool Robotic Telescope and the giant William Herschel Telescope, located alongside many others on the island of La Palma in the Canary Islands, high above most of the clouds. With telescopes like these, the planets that caused the Greeks so much trouble are revealed in all their wondrous beauty. We can now see them in glorious detail. We now know that some of those pinpricks of light we see are not planets or stars, but entire galaxies, each made up of billions of stars, and that we are just one of billions of such galaxies stretching across a cosmos that is larger than the ancients could have ever imagined. We've put telescopes into space, giving us a new perspective on the universe. We've sent probes to other planets, and even observed the sunset on Mars.
Better tools means better evidence, and this helps us develop better theories of how the universe works. The oldest of the sciences has come of age, and there's never been a better time to be an astronomer. Of course, there are some people who say that what we have learned has shown us that we and our planet are insignificant on the vast scale of the cosmos, but as far as we know, we're the only planet that's trying to understand how the universe works, and for me, that makes us special.
Okay, so hopefully then we've seen how we've got the how the history of our understanding of the solar system has changed, and you know, we know that what the ancient Greeks did use to observe the stars and the planets, their naked eye, that's all they had. They would have had a good clear view, but they only had the naked eye. And the problem with their model was that, the fact that if you put the Earth at the centre, and obviously, in their days the Earth was at the centre of everything, it became more and more complicated. The more observations they were able to make with their naked eyes, the more they had to put circles upon circles upon circles, and couldn't explain things, and it got extremely complicated. But the model, did change with Copernicus and then Johannes Kepler later on. So we've got these key players at the top, starting with on the right, Aristotle, ancient Greek philosopher. Then we've got a fellow called Ptolemy, we'll talk about in a second. Then we've got Nicholas Copernicus, Johannes Kepler, and then Galileo Galilei, as a slightly older man than he was in the video. So that's what we're up against for these ones. If we look at Ptolemy, who is credited with coming out with a sort of the first proper model of the solar system, and look at the time that he was around from 100 to 170 AD on that time frame, and he puts the Earth at the centre of there, with the moon orbiting it, and then the other planets, and then the sun. And he had the sphere of fixed stars. So he saw that the solar system was actually sitting within a glass sphere with all the stars stuck to it. To explain the fact that the stars seem to rotate round planet Earth as we see on time-lapse photographs on that video. He had them all attached to a big glass sphere that we were within, and that rotated and took all the stars with it, whilst all the solar system components all orbited round the Earth. So that was termed the geocentric model. Geo meaning to do with the Earth, geology, geography. Geocentric puts the Earth at the centre of the universe. The universe in that time, it wasn't the solar system, it was the whole universe. And the planets, the sun and the moon, all orbit the Earth. And they moved in tiny circles around the Earth, and these were these orbits of things doing that. But planets were attached to these crystal spheres, but the outer sphere had the planets attached to it, and that moved around as well. So that was a geocentric model that is attributed to Ptolemy, and we need to know about that one. Now later, our friend Nicholas Copernicus in Poland, working as as a proper scientist and astronomer, and if you look at the time delay, that from 100 to 170, we are now 1,400 years later that Copernicus came up with his model, which is known as the heliocentric, I should say, the heliocentric, putting the sun at the centre. And he worked on the work of other scientists, and he was a proper scientist. He used what evidence was available to him, and he looked at the work of other people, and he came together with his model, that was more simple than Ptolemy, with these endless circles and all the geometrical things that were complicated. And he said, right, okay, the Earth and the 6 planets, there were only 6 in those days, had been discovered, went round the sun. So he had the sun at the centre of this heliocentric model like that. And the planets that he knew about, again, these are ones that could be seen with the naked eye of astronomers. Mercury, Venus, Earth, Mars, Jupiter, Saturn. They were the planets that existed, and he had them orbiting the sun, with the moon orbiting the Earth. And that was his heliocentric model, which he proposed, and Johannes Kepler, worked with him and later modified that one there. So to summarise, we've got these two distinct models of the solar system. Ptolemy, it was the universe in those days, they thought that was the whole thing. But Ptolemy, geocentric, and Copernicus, heliocentric. They're the key players, and those are the key names and the properties of what was going on there. And diagrammatically, you can see the geocentric version with the Earth at the centre, top left, and bottom right, you've got the heliocentric version with the sun at the centre, which is the model that we accept these days. So on your lesson map sheet, what I'd like you to do, or if you haven't already, do that, is to fill in the information of these, the names of the models, the basic description of what the model involved, and then, because you're clever people, how is our current model, what we understand in the 21st century, the solar system to look like, how is that different to what Copernicus thought about in the 15th century? So just pause the video, get those filled in, think about the challenge question, maybe jot a couple of ideas down, and then when you're ready, resume the video. Okay, so hopefully we've got Ptolemy's is the geocentric model, spelling's interesting, and Copernicus is the heliocentric model. Geo meaning Earth at the centre, helio meaning sun at the centre. In terms of the model, geocentric, Earth's at the centre of everything, and again, in those days they thought it was the whole universe, but the Earth was at the centre, and everything was orbiting around it in perfect circles, with the sun orbiting around it as well. Copernicus, however, had the sun at the centre of the solar system, with planets orbiting around the sun. Now, hopefully, some of you knew, and from what you've heard this morning already or today, you've heard that what else is different today in the 21st century about the solar system. So you could have said that the fact that we've got elliptical orbits, it's not circular orbits. There are more planets and moons, and there are no fixed spheres that the stars sit on. They're all part of different distant galaxies that make up the universe. So we have changed a bit since then. Science evolves over time. Galileo made some key observations, which hopefully you picked up from the video. He credited with inventing the telescope, and not only inventing the telescope, but he actually pointed it at the sky and observed the absolutely critical things, that Jupiter seemed to have its own moons. And that was his observation. He didn't prove that everything orbited the sun. All he showed through his observations that Jupiter had its own moons that orbited Jupiter. And that was the thing that proved that not everything orbits the Earth. Because if these moons are orbiting Jupiter, clearly everything doesn't orbit the Earth. So he didn't disprove the geocentric theory, which is an easy trap to fall into. He just simply showed, that not everything orbits the Earth, and he didn't validate the heliocentric model. It was much later we worked that out. But his observations were absolutely critical. That Jupiter had 4 moons, and therefore, because they orbited Jupiter, they did not orbit the Earth, and therefore the heliocentric model really wasn't up to much anymore. So in terms of end of part 1 of this, hopefully we've got methods about how observing the universe has changed over time, from the naked eye to the most basic telescopes to then much more advanced telescopes and the use of computers and photography to preserve what we see. And obviously that those are critical developments. And we've also seen how the models have changed from the ancient Greek times of Aristotle and Ptolemy with a geocentric model, to Copernicus and Kepler, aided by Galileo's evidence, that we've now moved to what we believe to be, and know to be, the heliocentric model with the sun at the centre. By now we better know the names of the 8 planets in the right order as well. Okay, so we'll stop there for part 1, and then we'll come back with part 2 and look at some other things to do with the solar system.